Chapter 5 is on electric charges, and so here's what's in store for the next 4 lectures. By the way, we will have a lecture this Thursday because we missed yesterday's lecture. So here's what we'll do. The next 4 chapters will introduce electric fields and electric charges in this chapter. We'll talk about Gauss's law next chapter. Gauss's law shows you how to calculate the electric field when you have a uniform distribution of charges. Okay, a uniform symmetric distribution of charges. Then we'll talk about electric potentials, and then we'll finally talk about capacitances. But anyway, these 4 chapters comprise what is called electrostatics, meaning the charges are at rest. They're not moving. So that's what this 4 chapters will be about. And then after that, what we'll do is we'll get the charges to move, and that's what's called a current, and we'll see the effects of all of that. Okay, so the next 4 chapters are the subject of electrostatics, charges that at rest. Okay, so we'll talk about electric charges, we'll talk about insulators and conductors, Coulomb's law, and charge conservation. Okay, so here's a graph that shows you various materials. What this is showing you is materials on this side, all atoms are neutral, but all atoms and molecules are neutral. But materials, these materials like electrons, and these materials give up electrons easily. Okay, so these electrons wouldn't mind having extra electrons, and these guys wouldn't mind giving electrons up. And so, for instance, if you rub this material against any of these materials, what that do is these materials would grab electrons from these materials. So for instance, if you rub a rubber balloon against your hair, what will happen is rubber will grab some of the electrons from your hair will become positively charged, and the rubber balloon will become negatively charged. Okay, so, and if you did this with Teflon versus glass, the charge buildup would be even greater. Teflon with rabbit fur, that would be quite a bit of charge as well, and Teflon against human skin, right? So let me show you a demonstration of that. Oops. Okay, so here's what we're going to do is we're going to rub rubber against wool. Okay, so what will happen is the rubber balloon will grab electrons from wool, and will become negatively charged. So here we go. Here's rubber against wool, and you see it became negatively charged. And if I let go of it, of course, it'll get attracted toward towards the wool sweater. Okay. Now let's do this with 2 balloons. So I'm just going to grab just a bit of charge. And then take this. Okay, now we have them both charged, and you see the 2 negative charges repel each other. Oops. And they get attracted toward the positive charge. Okay, so that's what that thing is showing you. Various materials, how to charge materials. Now the thing is, only you learn in this chapter that the electromagnetic force, now we're talking about electrostatic force, but electromagnetic force is quite a strong force. And when you separate charges, you're only grabbing very few electrons. Okay, well, no, very small fraction of the percentage of electrons. Okay, so all right, as you all know, like charges repel each other and unlike charges attract each other. So two positive charges will repel each other and two negative charges will repel each other, and a positive and a negative charge will attract each other. Okay. So here the simulation showing this. So here's a here are two positive charges, and you see they're repelling each other, and the repulsive force is radially outward. Okay. And the closer you are, the stronger the repulsion. Okay. And what this is showing you is, we'll talk about electric fields. A positive charge creates an electric field all around it. Okay. And so the deal is how, so for instance, if this charge was here in Palm Coast and that charge was in New York, the question is, how does this exert a force on a remote charge? And the way we explain that is, what this charge does is it creates electric fields all around it. So it's created an electric field at that point as well. And this charge is just feeling that electric field. Okay. All right, so here's a negative charge attracting a positive charge. And again, like we've said, the closer the charges, the stronger the force. Okay. And this is showing you the electric field created by a negative charge. Here are the numbers. Electric fields are measured in Newton per Coulomb, and you'll see that this is equivalent to volt per meter as well later on. And the force, of course, is measured in newtons. All right, so like charges repel each other and unlike charges attract each other. Okay. We'll briefly talk about insulators and conductors. Conductors are, we're talking about electric conductors now. And then there will be thermal conductors and thermal insulators, but we're talking about electric conductors. Conductors are, most metals are good conductors. Conductors are materials that have free charges. So conductors are materials with free charges that move freely. And if you connect a voltage source like a battery to them, they'll let an electric current pass through them. Okay. So let me give you a sort of a picture of conductors, a brief diagram. So let's, all right, so here, let's say this is a metal. Like I said, most atoms, well, all atoms are neutral. In a metal, what happens is each of these atoms will let go about 2 of the outermost electrons. Okay, and so these electrons move about, are free to move about in the metal. Okay, so and and the positive ions are fixed in place. Okay, so, and that's what a conductor is. It has these free charges that are free to move about. And if you connect a battery to this metal, what the battery does is it'll establish an electric field in the metal. And well, you'll see all of this in a bit, but the electrons move in response to the electric field. And so electrons will move in this direction. Again, this constitutes a current. So you'll have a current moving in. All right, so this is a, so again, so let me do a cleaner picture. So for a metal, now I want to draw the positive ions. You have a bunch of free charges moving around in the metal, okay, in a background of positive charges, okay. And so metal has free charges, okay, and that's why they have conductive properties. All right, in an insulator, in an insulator like rubber or wood or something like that, all the atoms hold on to their electrons, and so there's no free charges, and so that's why this is not this material is not a conductor, an electric conductor. Okay. Now here's another way to look at them. Okay. So you will do a lab. You will do a lab using this simulation. Okay, it's the conductivity lab. So here's a metal. This is the band structure view of it. Okay, so this is called the conduction band. This is the valence band. Okay, and you see this valence band is, well, okay, all right. Maybe the terminology might be different. Anyway, so here's a. Okay, so in a metal, you see this band, the topmost band, is partially empty. Okay, so for the electrons to move about, what you need is a few empty levels. Okay, and so now if they have few empty levels, you apply a voltage and these electrons can move about. Okay. So the electrons can move about, and the larger the voltage, the more electrons are in play. Okay. So the larger the voltage, and you get a current moving. Now let's look at what is the difference between a metal and a plastic. So in a metal and a plastic, you see in a plastic, there are no empty levels. All the levels are full. And so the electrons cannot move. You have a voltage you've applied, and there's no electric current passing. Okay. Now let's look at a photoconductor. Okay. So let's look at the plastic and the photoconductor. The difference in plastic and the photoconductor was the following. Okay. In plastic, this band gap was quite large. Okay. So the idea is the following. Now, if the band gap is small, if you could excite these electrons into these levels, then you could have the material conducting. And that's what this light could do. And generally, it'll be UV light or something like that. So if you shine this beam of light, now these electrons were able to jump to these empty levels and were able to conduct. Electricity. You see, you got a double whammy because some of the electrons jumped over there. You had some empty levels here, empty levels there, and so you got quite a bit of conductivity. These materials are called photoconductors. Semiconductors have similar properties. And they'll have impurities in them, roughly around there, and those electrons can be excited easily, thermally excited into empty levels. Okay. So here's another point of view of, conductivity, okay? So, and the difference between insulators and conductors are conductors have free charges, insulators do not have free charges. And semiconductors have electrical properties between insulators and conductors. And for semiconductors, their conductivity can be varied by the number of impurities and so on. Okay. So in semiconductors, the number of charges can be changed with impurities as well as temperature. This is just a little charging by induction. So here's a piece of metal. You bring a charged rod. So this is negatively charged rod. And so you chase away the electrons on the other side. And if you ground the electrons, this can become positively charged. So here you've charged this metal spear without actually touching the rod to the spear. Okay. All right. Yeah. So now we'll talk about the force between charges. Mr. Coulomb figured out the magnitude of the force between charges, and here is the formula. and the force between charges is a constant, which we now call it as Coulomb's constant, times the product of the charges divided by the distance square. Okay. The magnitude of Coulomb's constant is 9 times 10 to the 9 Newton meter square per Coulomb square. So anyway, the force depends on the product of the charges divided by the distance square. Okay. So if the two charges are positive, or if both the charges are negative, the force will be positive. Okay, so the force is repulsive. This is just giving you the magnitude of the force. Okay. And Mr. Coulomb used this apparatus. It's called a torsion balance to figure out this force law. Okay. So it's known as a torsion balance, and he figured out the loss sometime in the 1760s or so. Okay. So the force is proportional to the product of the charges and inversely proportional to the distance square. Okay, just to give you a sense for how strong the electric force is, so let's look at the hydrogen atom. So here's the hydrogen atom with one electron going around the proton. Now there's a gravitational force between the two, and the gravitational force between the two is G, mass of the proton, mass of the electron divided by R squared. And there's an electrostatic force between them, which is given by, and the charge of both the electron and the proton are the same. So it's E times E divided by R squared. And you can calculate the ratio of the two forces. So if the question is, what is this ratio? Okay. So what we're saying is, how much larger is the electrostatic force compared to the gravitational force? Okay. And that's what the slide shows you. It's 10 to the power 40, 10 to the power 39. So the electrostatic force in the hydrogen atom compared to the gravitational force is 1,000 trillion times stronger. Okay. So the point of this is, if at all there's an electrostatic force in play, in most situations on the Earth anyway, you can totally ignore the gravitational effects. So if the electrostatic force is in play, okay. So anyway, that's the point of this. Now, if you were close to a black hole, then the gravitational effects could be significant. Okay. Now here's a second example of how strong the electrostatic force is. If you took 1 kg blobs of proton, okay, so what does that mean? Let's see. Okay, let's say, so here's 1 liter, and this is just roughly 1 liter. 1 liter is a quarter of a gallon, roughly. Let's say you have 2 water bottles like this, and if you can, they're filled with water, and if you can strip them of completely of their electrons, which would be almost impossible to do. Well, very, very hard to do. Anyway, so if you could strip these this bottle of water of its electrons, they would all be positively charged now. Okay, so roughly 1 kg of protons. Now we're ignoring the fact that half of them are neutrons, but they would repel each other with a force equal to the weight of the Earth. Okay, so that's what this is saying. So you could calculate the force like that. There's the Coulomb's constant. You separate them 1 meter apart, and So the calculation shows 1 kg, there's the mass of the proton, 1 kg divided by that gives you the number of protons, there's the charge of each proton, and there's the force of repulsion between them. Okay, so the electrostatic force is enormous. Okay. Now, here's the superposition principle. What it says is if you have multiple charges involved, let's say you want to calculate the force on this charge. To calculate the force on this charge, calculate the force of this guy on that charge, which is that, and then calculate the force on this guy due to him, which is that force. And the net force on this guy is just the sum of these two forces. Okay, so the superposition principle essentially says if you have multiple charges acting on a single charge, all you have to do is calculate forces pairwise independently as if the others are not there, and then add up, take the vector sum of all the forces. Okay. So that's the superposition principle. So for instance, here, 8 charges, 1, 2, 3, 4, 8 charges surrounding this charge. And to calculate the net force, you calculate the force due to each one of them and then add up all the vectors, I guess. So, and you can do this for as many charges as you want. Okay. So that's the superposition principle. Now here are the 4 fundamental interactions. It turns out that in nature, there are only 4 fundamental forces. There's the strong force, electroweak force. The electroweak force is comprised of the electromagnetic and the weak force. We are studying part of this electromagnetic force. We are only studying the electric part of this electromagnetic force right now. And then we'll study the magnetic part of the force later, but so we are studying part of this force now, weak force, and we've studied gravitation in physics 1. Okay, so there are the 4 forces: strong, electromagnetic, weak, and gravitation. These 2 forces have been combined into a single force, so these 2 forces behave like a single force at high energies. All right, this shows you the relative strength of these forces. This gives you the range of the forces. And in quantum mechanics, forces are mediated by particles, and this shows you the mediating particle. So if the strong force, let's call it strength 1, the electromagnetic force is 100 times weaker. Okay. And the weak force is 1,000,000 times weaker than the strong force. The gravitational force is 10 to the power of 43 times weaker than the strong force. So the gravitational force is extremely weak. Okay. Well, the strong force is very strong, except that its range is very small. It's 10 to the minus 15 meters. Okay. And the electromagnetic force has a range, infinite range. And the weak force has a range even smaller than the strong force. It's 10 to the minus 18 meters. And the gravitational force, of course, has an infinite range as well. Okay. So the mediating particles are gluons, photons for the electromagnetic force. For the weak force, it's the W and Z bosons, and for gravity, it's postulated as graviton. We haven't detected a graviton. And some people don't believe in gravitons, but anyway, so that's the picture. Okay, now, so this thing, these 2 facts explain the structure of an atom. So, for instance, let's ask the following question. So, you saw that. Let's build a carbon-12 atom. C6 carbon-12. So here's a carbon atom. Well, it has 6 protons, 3, 4, 5, 6, and let's put in 6 neutrons, 5, 6, okay. And then it's got electrons. Okay. Okay. Now the question is the following. So you have these protons, and by the way, so the size of a nucleus is the size of this nucleus is about 10 to the minus 15 meters. Okay. So the question is, here are these two protons that are so close to each other, and they're of course repelling each other very strongly. Okay. So why aren't they flying apart from the nucleus? Okay. And so the mystery is solved by now this, because they're that close, there is a strong force between them, and the strong force is what's holding them together. Okay. And the strong force, remember, is 100 times stronger than the electrostatic force. All right, so if you want to build a nucleus, okay, you would have, the size of the nucleus has to be roughly that, because the strong force has to overwhelm the electrostatic repulsive force. And so that tells you the size of the nucleus of an atom. Okay. So from this table and from the range of the strong force, you could surmise that. Okay. All right. So anyway, here's the sort of holy grail in physics. Electricity and magnetism were combined in the 1850s. Okay. So right now there are 4 forces, and we hope to have the hope is that at extremely high energies, they would all act as one force. Okay. And so electricity and magnetism were combined in 1850. The electromagnetic and the weak force was combined in the 1970s. And right now, the strong force behaves like a separate force. The electroweak force, strong force, and gravity behave like separate forces. But the belief is at a high energy, we could find a single force that would explain things. Okay. All right, let me pause, and I'll let you guys ask questions. Okay.